back. We'll get started in just a second. Today, Chris and Julio are going to be teaching us about differentials and linear approximation. But give me just 1 second. I'll be right back. All right, guys, sorry about that. Thank you for your patience. I think we are ready to rock and roll. We got everybody here. Oh, it's mine. You like this? This is so annoying. So I'm going to go ahead and make Chris and Julio co-hosts so that they can share their screens if they need to. I think, though, you guys, I know Julio sent me some final versions of the videos, and those look awesome. Chris, let's see, do you want to, yeah. Remind me, Chris, did you have everything published in a video that you wanted me to show?
No, I just have a PowerPoint.
Okay, so I will hand it over now to Chris and Julio. If you guys want, I can stream Julio's video from my end, or you guys are both now co-hosts, so you can share screen and stream from your end, whatever you'd like to do.
Sweet. So I will start with 1 second.
Awesome.
Okay. Can everybody see that?
Looks good.
Okay, so linear approximation. So what is linear approximation? Linear approximation helps us approximate a value as long as we're near the point a comma f of a. So the further we get away from this point on the graph, which I'll get more into, the worse our approximation will be. Just kind of keep that in the back of your mind. How do we do it? In order to find the in order to approximate a value, we're going to use tangent lines. A curve lies very close to a tangent line. The closer and closer and closer you get to the point of tangency. So as we can see here, I'm kind of using this graph as a parent graph. The point f of a, which is right here, the closer you get to this point, it's very similar to the curve or the function f of x. And the farther away you get from this point, such as over here, the y values are very different. But as you get closer and closer, it gets very similar. So we use that to approximate the value of something very close to this point. Tangent line approximations, the equation of the tangent line to the right would be y equals f of a plus f prime of a times x minus a. To approximate a value, we're going to use this equation. The equation f of x is approximately the equation of the tangent line. And then just some vocab that the professor wanted to make sure we understand. L of x is called the linearization of f at a. Okay, so we can, oh, hold on. Why didn't that work? 1 second, sorry. Okay, it's fine. Okay, sorry, it was supposed to be, we're supposed to see all the, okay, but this is an example of a problem, so we can just run through it. I don't know what happened to the animations, but we can just run through this example if you guys want to write this down or you want to slowly go through it. Finding the linearization of the function f of x equals the square root of x plus 3 at a equals 1. And we're going to use that to approximate the values of the square root of 3.98 and the square root of 4.5 or 4.05, sorry. So we're going to first find f f of a. So we're just going to plug in a to the function f of x, which we can see we get right here. We get square root of 4, which equals 2. Then we're going to find f prime of x, which we just find the derivative of f of x, which we all know how to do that now. So we get 1 over 2 times the square root of x plus 3. And then we're going to take that and find f prime of 1 because we're using a equals 1, which then we plug in 1. We plug in 1 right here to the x. So we get 1 over 2 times the square root of 4, which is just 2 times 4. So we get 1 over 4. Then we're going to plug that back to the original equation up here. So we have every single piece. So we get y equals 2 plus 1 over 4 times x minus 1, which is equal to 1 over 4x plus 7 over 4. So then we then use all of this, and then we can find the approximate values of the square root of 3.98, which we can see right here.
So this is good. Does everybody see what's going on? The line there where he says plug into equation, that is the tangent line or the linearization of this function f of x at a equals 1. So right under where it says plug into equation, that's the thing that we can use to approximate the square root of x plus 3. As long as we stay close to the base point a, which is 1 here, we can plug in any x values we want. And that will give us something that is very, very close to the square root of that number plus 3. So if we want the square root of 3.98 or the square root of 4.05, we just have to plug in the x value that would get us those things in the actual function. So for example, in the 3.98, what x value would give us the square root of 3.98? Well, if you look at the function f of x here, it's the square root of x plus 3. So to get the square root of 3.98, we would be plugging in 0.98 for x. And 0.98 is close to 1. So we can trust that this is a good approximation and then just follow the formula from the linearization. That's exactly what he's doing here. This is beautiful.
Yeah, so exactly. So the main point right here is 1. So like if you go back to this, not that. If we go back to this graph right here, you can see we're trying to get very close to this point, like you said, a point of A. So we want to stay very close to 1 here, which is exactly what we did, 0.98. And then for 4.05, we stayed to 1.05, which is very close to 1 also. So then here's another example. This is a little different. We're trying to, it's the same thing, but it's an easier example, I think. It's just we're trying to use it to estimate the value of f of 37, which f of x equals the square root of x. So we're just trying to find the square root of 37 using the square root of 36. So it's this, you can see, we can run through this again. So we're going to find f of a, which is square root of 36, which equals 6. And we find f prime of x, which is 1/2 times x to the negative 1/2, which is 1 over 2 to the square root of x. And then we are going to find f prime of 36. So we just plug in 36 for x right here, which is 1 over 2 times the square root of 36, which is 1 over 2 times 6, which equals 1/12. And the same thing, we're going to plug into the tangent line. Then we're going to get 1 over 12x plus 3. And then when we plug in a, we get 6.0833. So does anybody have any questions on linearization?
I think this is very nice. Just for fun, maybe we can tab over and calculate the square root of 37 using a calculator and see how far off we are. We should be pretty close.
Absolutely. Let me see. That's something I'll let you see. 1 second.
Yeah, no stress.
So, So yeah, it's very, very close.
Nice. Yeah, this is fun. So this linearization stuff it's a powerful tool, right? If you had to calculate these numbers on a desert island, or if you needed to know the square root of 37 accurate to 3 decimal places for the purposes of some sort of engineering project, you got it. You got it right here, and it's not terribly hard. Something similar to this is actually what your calculator does when you ask it for weird square roots. Which we can talk about those in Calc 2 when we learn about Taylor expansions, but these are the first few terms. This is very nicely done. Thank you.
Absolutely. So that's basically it about linearization, or linear approximation, sorry. So I'll give it to Julio now to share his video. Oh wait. Oh yeah, sorry, I'll go back to that. But she got, okay, never mind.
Now you guys will want to practice going through that by hand. It does take a little bit of time to get familiar with the formula. Just remember that it's the same formula for a tangent line. So you're essentially finding the tangent line and then plugging in an x value. But make sure that you solve one or two of these problems by hand carefully, and you can follow the examples that Chris used here as a kind of model.
And I can send anyone this PowerPoint if anyone would like this too.
That's very nice of you. All right, looks like Julio's getting ready there. Whenever you are ready, go ahead and unmute yourself. And then I took a look at that latest video this morning. It looks really good. We're in for a real treat here. He's put a lot of nice work into this.
Right. So yeah, you could just go ahead and stream it from YouTube.
Okay.
Yeah.
Alrighty then. I'll go ahead and turn on my screen share then. And we'll go, where was it? Here. This was the most recent, right? Yeah. Okay. Alrighty, I'll go ahead and play this here.
Like, is there no audio?
Everything okay? Or you wanted me to just let it play?
But there should be audio like by now.
Oh, can you guys not hear it? That's not good. So I can hear it on my end, but if you guys aren't hearing the sound, what could be going on?
Yeah, I'll go ahead and check that out right now.
Okay, that's so weird. Let me try playing it out of my speaker. I guess we can try this. Here, let me know how this sounds. I'm gonna back up the video. I'm turning my screen share back on.
So, hey guys, as you already
Is
know,
that better?
my name is Julio, and today I'll be covering differentials. So, as of right now, we're gonna do a quick review of derivatives, just to make sure that you guys are comfortable with it, because it does kind of go apply into differentials as well as linearization. So we're just gonna cover that real quick. But now you should have a good understanding of what is meant when we say to take the derivative of a function at x equals a, where a is a constant. That is to say that f prime of a. You also already know the definition of a derivative is right here, that the limit is equal to 0 of f of expectation of f of x over h. You should also know that h is you could think of h as the difference between the points, as I stated here. You could go ahead and read this, but I don't necessarily want to just be reading everything that I wrote, because then I don't really have to talk. As you already know, this derivative, and as we take a secant, you know what a secant line is the line that crosses 2 points. You know that as we take the distance between those 2 points closer to 0, in this case that will be h, that will pretty much become a tangent line at x equals a, and then that would be the slope of the tangent line, as we have here on the second definition. So Chris already covered linearization, but this is just a quick review or summary of what he said. We know that linearization is pretty much like when a tangent line at a point x equals a starts to resemble the graph, in this case f of x, as we get closer and closer to a, because the differences in the y values and the distance between the y values becomes smaller and smaller as we approach a. Therefore, we say that f of x is approximately equal to, in this formula right here, f of a plus f prime of a times x minus a at x equals a would be the formula for the tangent line approximation. I would show you that graphically in a couple of minutes. So by now, you might be wondering, what are differentials? In short, differentials are just variables, independent variables that could be assigned any number. In this case, I said that just like x, b, a, and f, or any other letter could be assigned a value like 5, 10, 0.1 in this. In mathematically, we would assign dx a small value like 0.1, but I'll talk about y later. That's just what differentials are. But in this case, dy, it's pretty much, it's the difference between the y values. It's related to delta y, but I'll show you that y later. But in this case, dy is like directly affected by dx. I like to think of this as a cause and effect relationship, because dx could be the cause, and then dy is the effect. dy is directly affected by dx.
That.
And as you already know, dx and delta x and dy and delta y are approximately equal to each other, because of what you're going to see later on why this is the case. Then right here, I pulled a graph of visual representation from the textbook, so you can more or less see what's going on. In here, the textbook says that dx is equal to delta x. That's a easy notation. But in graphically, yes, dx and delta x are indeed the differences between a point x and a point x, comma f of x, and a point x plus delta x, comma f of x plus delta x, which in this case, we could see that point here to be q. The dx and delta x are the differences in the x value between those 2 points, whereas delta y, as you can see already here, are the differences between the y values of those 2 points and dy is rather the differences between, you could say, where x is equal to x plus delta x, but where it stops at the tangent line. So in other case, that point is the difference, dy is the difference between r and s, not q and s. That will be delta y. But these two are relatable to each other. They're related to each other because, as you will see later, when we take dx or delta x closer and closer to 0, so like say a very small value like 0.0001, dy becomes pretty much almost the same thing as delta y. Like they become very close to each other. And that difference between them just pretty much almost disappears completely, but they're not equal to each other. Dy and delta y are not equal to each other. We could also see here that the slope of the tangent line could be represented as dy over dx. And as dx goes closer and closer to 0, like the derivative, that slope, we will get the slope of the tangent line at a equals x. I mean, as x equals a. So that will be like at this point right here. So right now I'm going to leave the PowerPoint so that I could show you more of this graphic. So then in here, we actually are using decimals to show you more or less what we mean by taking the x closer to 0 and how that affects dy and delta y. Over here on the left, you guys can ignore all of this. This is just how I came up with this thing. I had help from a friend. His name is Alexander. I'm gonna give him credit.
It's really nice.
So dx, as you can see, is the difference between, in this case, the point A at a equals 1 and at a equals, and at a plus dx, which in this case is 1.6, but that would change as we change around dx. We could see here that as we make the difference between those 2 points bigger, a remains the same, of course, but dx changes because, sorry about that. Dx would change because we're increasing the distance between them. And as we decrease the distance between them, you can see how the graph, this dashed line right here is a tangent line approximation at, in this case, at x equals a, but a is equal to 1 in this case. So you could see how as we move, as we make dx smaller and smaller, in this case, I'm actually gonna go ahead and make it really small. See how pretty much it becomes the tangent line, like that the tangent line becomes the slope at that point, x equals 1 in this case. And you could see how right here, I'm not showing you dy, but dy will be I guess you could call it an extra amount of differences between, it'll be delta y, but up to the point, up to this tangent line approximation. So it'll be like up to here. That would actually be dy. But you could, let me zoom in, you can see it better. See that as we take dx closer and closer to 0, then you see that the difference between the tangent line, I guess you could say, if this is a point, let's call this point S, and this point right here, let's call it point R. The difference between those 2 points becomes smaller and smaller. And you will notice that it actually becomes very close to the difference between this point right here and then this point right here, also known as, like, that would be delta y. So you can see, like, look now, I'm saying 0.1. So then if you look at it now, look at what happens right here. The difference is very, very small. To the point where the difference between this point and this point is now like way smaller. And as you can see that we take dx closer and closer to 0, that difference will become smaller and smaller and smaller and smaller. and pretty much then dy would be not equal to delta y, but very closely related, very closely equal to it. Yeah. So then, say I give you a function x squared, and I were to ask you a question, what's the derivative of x squared? Well, you already know that's 2x, right? Sorry about that. Right, so then you already know the derivative of x squared is 2x, then that would be 2x is also known as the slope dy over dx at x equals a. It will be the slope of a tangent line at a point x equals a. So if I ask you to just give me what is the change in y or dy only, I just want to know what is the change in y, nothing else, then you would just solve for the equation dy over dx equals 2x, which would give you dy is equal to 2x times dx. As you can see here, dx and dy are differentials. And since this works for x squared, it also works for any differentiable function, where that we get the equation that dy is equal to f prime of x times dx. That also means that delta y is approximately equal to f prime of x times dx, because delta y is approximately equal to dy. So then here are a few examples of how would we apply this concept to actual functions. We have that in this case, if y is equal to cosine of x, then using the previous function, the dy is equal to f prime of x times dx, we get that in this case, dy is equal to negative sine of x times dx. In this case, we have if u is equal to x cubed plus 3x, then applying that formula, we have that du is equal to 3x squared plus 3 times dx. It's just the derivative of the function times dx. And then in this case,
I'm going to pause for just a small second here. So Julio's doing everything beautifully. This is perfect. There's two perspectives that this section presents, right? And the one is like the approximation perspective. And so far, what Julio's been talking about in this section is kind of connecting the approximation perspective to the notation of differentials. Down the line, this notation on its own will kind of be important. So just the idea of getting comfortable going from y to dy, where you are just taking derivatives and then multiplying both sides by dx, but writing it down like this right away, dy is negative sine of x dx, it might seem trivial, but this is actually the thing that we're going to use later. This is the part that we're going to build on when we start talking about integrals and substitution in section 5.5. So I just wanted to pause for a second here to say that this piece is the piece that we will build on later.
E to the 2x, then z is equal to e to the 2x, then dz will be equal to 2e to the 2x times dx. So in here you can see that, let's say in this example, for instance, if du is equal to this, then that would also mean that then if we solve for du over dx, and we want to know what du over dx is equal to by dividing dx from both sides, we would see that du over dx is equal to 3x squared plus 3. And that's an example, so we could derive at that. And this is related to related rates. And as you can see, it's also related to linearizations.
Very good.
So then, but now you should have a good understanding of what we're trying to say when we talk about differentials and also related rates as well. But just to get extra practice in, say I were to ask you, what is the differential dy if I give you a function y is equal to x cubed, and I let you know that x is equal to 2 and dx is equal to 0.02. I would like to remind you that dx is indeed the difference between the 2 points I already told you, which is why we normally want to take dx to a very small value, and And then in that case, I did that here so that I can show you how dx is related to, how dy is related to delta y. But technically, dx could literally be anything. It could be 100, 5, 10. In this example, I used a formula as solved for dy, and we got that dy is equal to 3x squared times dx. So then by plugging in 2 for x and dx as 0.02, we get that dy is equal to 0.24. So then we know that the difference between the y values in the function is 0.24 when the difference in the x value dx is 0.02. Also when x is equal to 2. So then say if you want to find delta y, well, you could use the formula of delta y is equal to f of x plus delta x minus f of x, which is just the difference between the point within the y values of the point x plus delta x and the y value between the point f of x. Sorry about that. Right, so then as I was saying, in this case, dy would give you 0.24, but if you use this formula down here, you will get that dy will give you 0.2424. And as you can see, these are not equal to each other, but they are approximately equal to each other. This, of course, only happens when dx is a very small value. And as a matter of fact, if dx was to be smaller and smaller, say instead of 0.02, we say that dx would be equal to 0.001, or even smaller than that, then these values will become even closer to each other. On slide 4, I wanted to talk about something interesting. So when I first introduced, and I should have talked about this then, but when I first introduced the x and the y, I kind of got confused when I was first doing this because they talked about the instantaneous rate of change. And after studying this, I came up with, I like to believe that there is no such thing. If I take a picture of a car, show it to you, and ask you how fast is the car going, you will literally look at me confused, the car is stopped. It's literally not moving at all because it's not even a video, it's a picture. So what's happening is it's a rate of change. There's we're taking a rate of change between 2 points in time at which the car has traveled a certain distance, where the difference in time between these 2 points is extremely small, but not 0. So that's what we mean when we say instantaneous rate of change.
So I really like what you said here, and this was something that made me smile a lot when I watched this, is that you have this perspective that there isn't really an instantaneous rate of change. It's just a rate of change over a very, very, very small interval of time. What Julio's presenting there is an opinion that is a little bit different than what we teach in this class, but is accepted among a number of mathematicians called ultra-finitists, who really aren't a fan of limits where you send things to 0, or the idea of infinity. And the intuition is really good, and it's the perfect way to think about this section, because we're thinking of the derivative as an instantaneous thing, but really we get there as a limit, right? We're taking a limit as h goes to 0, where h is that distance. So thinking of dx as delta x and dy as delta y in this setting is okay. But in general, we need to think of dx as being infinitely tiny, and dy as being kind of infinitely tiny, whatever that means. And so exactly what he's saying here, that dx is approximately delta x and dy is approximately delta y, is a bit of an abuse of notation. That delta x and delta y are measurable actual changes, and dx and dy on their own are infinitely small and can only be really thought of as measurable when you divide one by the other. Because if you divide two very, very small things by each other, you get something of reasonable size. But each one on their own is kind of too small to work with. So we approximate them using delta x and delta y. I really like the way you said that. It's nice.
And that is all for my student teaching lesson. I hope you guys learned something out of it. I'm sorry if I was kind of nervous. This is the first time I do this, but
no, you did really good.
I always encourage you, if you want, you could go ahead and practice this. If you still are confused or didn't understand, you could go ahead and ask Professor Paustiger some questions about it, or you could go ahead and ask me directly. Thank you for your time, and I will end recording.
Okay. So let me pull out of here. First things, are there any questions for Chris or Julio about the, let me just turn this off, about their presentations? Any questions from the classmates here about what was discussed there? Yeah, which example would you like to see? Here we go. Let me turn this back on. We can come back a little bit. So here are the examples where we just calculated the actual du, dy, the differentials. And then the approximation examples, I think there was one earlier, right? Did we actually do an example with this guy? Let's see here. Oh no, that was later, wasn't it? Okay, sorry. So this one, right? So the idea here is they want us to use that kind of formula from the textbook to get an approximation for dy. And the idea is we begin with the differential, dy is 3x squared dx. And then we're going to plug in the bits of information they gave us. So they want us to use 0.02 for dx, 2 for x. So kind of like this is our base point. And then we're going to nudge by 0.02. And the upshot is you can plug that into this formula. So dy is 3x squared dx. So dy here would be approximated by 3 times 2 squared times 0.2. So dy there we could say is approximately 0.24. I can show you how I would write that, like if we were going through it. Let me write these things down, then I'll tab over. So if y equals x cubed and x is 2, approximate dy with dx equal to 0.02. All right. So this is the sort of thing that you might run into in the homework. The idea is along the graph of x cubed, right here we'll call this 2. If I were to nudge over by just a small amount, dx, so here would be like 2 plus dx, and this distance between them is dx. If we were to nudge over by some very small amount, how much are we going to end up going up? That's sort of the idea. And we get there by thinking of the function as locally linear. So we can approximate the value of the function up here using the linearization. That was sort of Chris's thing. And Julio's thing is saying, well, you can do a very similar calculation in terms of the differentials. So I can say, I expect the change in y along this graph to be about the same as the change in y along this tangent line. And I can use the derivative and the language of differentials to discuss the change in y along that tangent line. So this is our delta x, and this is our delta y. And dy is approximately delta y. So first, dy itself is exactly f primed of x times dx. That's the definition, which is, in this case, 3x squared dx. And so dy, I would say, is approximately, because we're plugging in an approximate value for dx here. Dx shouldn't really be 0.02. That's what we were saying about the abusive notation. But this would be approximately 3 times x squared times dx. Sorry, I don't know why I wrote those parentheses, those silly parentheses. And so with x equal to 2 and dx equal to 0.02 dy, this can still be an exactly equal to, then dy would be approximately 3 times 2 squared times 0.02. So I introduced the shaky equal sign at this step. We don't need it back here. But I'll introduce the shaky equal sign at this step to say, well, we're kind of like abusing notation. dy should be infinitely small. It's really delta y that I'm looking at here, or something very similar to delta y. It's a finite but non-infinitely small step size in y. But we're just plugging in, right? They gave us a value for x, they gave us a value for dx. So we're just going to take those and plug them into this formula. If I plug the 2 in here and the 0.02 in here, I get this, which is 12 times 0.02, which would be what, 0.24? And that's how we do the calculation. It's not too bad, right? The main things that I'm going to test you guys on, just as a little wrap up here, the main things you'll be responsible for are the linearization, and using linearization to approximate function values. When it comes to these sort of approximations, I really like the language of linearization a lot, because the language of differentials ends up involving some of this abusive notation. But then the differentials are important. So just calculating differentials symbolically. Things like if y is equal to e to the 2x plus x squared, then dy is equal to 2e to the 2x plus 2x times dx. So these are the sort of things that you guys will be responsible for in the exam setting. When it comes to the approximation of y values along the graph, I won't likely have you guys do that on a test using the notation of differentials, because the notation is so sensitive and it's frankly a little bit misleading to use the language of differentials there. So there you'll be using the linearization. Those are the things that I'll be asking you to use for approximation of y values on graphs. And then the place where you'll be using the notation of differentials a lot is when we just straight up calculate dy or dx or du or whatever, like this, where you take the derivative on the right-hand side here, and then you slap on a dx. It might seem like a trivial step, but believe me, when we get to U substitution in section 5.5, it's something that you're going to want to not only be able to do, but like visualize ahead of time without writing something down. That's really all I'm going to hold you guys responsible for from this section, as far as like testable material. So make sure you remember the formula for L of x from Chris's video. And from Julio's video, make sure you are comfortable doing these sort of calculations. But I also invite you to rewatch Julio's video, because he presents a lot of really neat things. The Desmos work there is excellent. It's a really good way to visualize the sort of delta y becoming like dy. And also the way he describes the notational issues, I think is very clever. Was that the example you wanted to see? And were there any other questions or comments? Okay, then I think we might be a little bit early still, but this is where we're going to go ahead and end it for today. Oh no, we're pretty close. We're right about on point. So this is where I'll go ahead and end today's lecture. Let's thank Chris and Julio for the awesome work they put into these. Really, really good job, both of you guys. Really nice presentations. Next Monday, Kevin is going to teach us how to find mins and maxes. So we're going to go through section 4.1. And then I think maybe next Friday, or somewhere around next Friday, we'll have our next student teaching after Kevin. But it's going to depend a little bit on how we get through the material next week. So next Monday, we're going to learn section 4.1, which is on mins and maxes. Between now and then, please work hard to finish up the homework that is here. I will include the differentials and linear approximation problems on next week's homework. That way you're not too overwhelmed. If you are stuck on anything, you can come see me in an office hour or send me a Canvas message. Otherwise, I will see you guys on Monday. Any last minute questions? Alrighty then, guys. Yep, normal office hours today. Yeah, really good work, guys. Thank you. Thank you very much for the time you put in and the quality products you put together. It's really well done. All right, bye, guys.